Okay, so let us begin. So, like I always say, you guys should invite more of your friends. If you guys are to be a little bit more than listen in the classes, then we'll also be able to do math as well. So, invite your friends as well. Free classes for everyone. So, let's begin. So, in this question, what are they saying? The same we have a record skiing speed of 203.1 kilometers per hour that was achieved on a mountain slope inclined downwards at 51 degrees. At this speed, the force of friction on the skier, see this is very important, air and sliding friction. So I'll come back to this statement. Balances the pull of gravity along the slope so that the motion proceeds at a constant velocity. Okay, so when you read the question, you must understand what is really happening here. But before we get back to understand what is happening, let's get a feel of what they are actually asking. In part one, they're saying, what is the rate at which gravity does work on the skier? So they're asking for a rate of which work is being done. So we know to say the rate of doing work, that just defines power. So we know they're looking for power. But power, which power? They're saying the rate at which gravity. So they're asking for the rate at which gravity does work. So in other words, they are looking for the work done against gravity or the work done by gravity. So we know the work done by gravity. Do you recall how we calculate that work? How do we calculate the work done by gravity? I think we've touched on it before. Okay. So we'll come back to it. We'll look at it as well. But that's even the easy part. That's actually the easy part. They've given us an answer here. So should we find something? We have something to compare with to see if our answer is correct and if our answer is if we have to revisit our calculations. So let's let me first try to describe the question so that you guys can understand what is happening here before we start working out this question. So what they're saying here is that we have this object, not that diagram. We have this object here that is sliding downwards. And they're saying that as it slides downwards, it achieves a record speed of 203.1 kilometers per hour. Okay, so what else is there? So it achieves that speed while moving downwards. And they're saying the angle of inclination, that's the angle down here, that's a 51 degrees. Okay, what else is there? At this speed, the force of friction on the skier, now you see, they say the force of friction on the skier. The force of friction is general. In this case, they are actually specifying that this person actually experiences air friction and also sliding friction. So the question actually specifies to say that there are two forms of friction that are being experienced here. One is from air, the other one is from sliding friction. You'll notice that later on, they will actually ask about these. Look at it part B. What is the rate at which sliding friction does work? So here we'll have to come back and observe that when they say friction, it's actually a combination of air friction and sliding friction. So we should be able to separate these, find sliding friction and also find um, air friction on its own. So we'll come back to that when we start looking at B. So at this speed, the force of friction on the skier balances the pull of gravity along the slope so that the motion proceeds at a constant speed. Now, with that description, let's try to just understand what is happening here. So consider this to be the slope. I would draw this as just an object, something like this. So this is our skier. Now we know to say the force of gravity that actually drags this person downwards, it will have two components. The component that drags the person downwards will be given by mg. You know this has to be sine theta. In this case, theta is 51 degrees. So of course, you know from forces how we resolve to get the component of the weight that goes down. At this point, in this statement, They're saying at this speed, the force of friction on the skier balances the pull of gravity along the slope. What is this saying? This is saying that, well, if we have the pull of gravity pulling this person downwards along the slope, and if the other side, we have the force of friction, because friction opposes motion, the question is saying that the force of friction balances the pull of gravity. What does that mean? It means that when the speed is actually this value, the two are the same, meaning force of friction is equals to mg sine theta. That's what that statement means. Again, we'll come back to this later on when we'll have to use it. I just wanted you guys to understand it. Okay, so we have got that part. So what else is there? So pull of gravity along the slope so that the motion proceeds at a constant speed. Again, constant speed, they're just trying to ensure that we end up in this state when you say sum of forces is equals to zero, because the constant speed means zero acceleration. So sum of forces is equals to ma at zero acceleration. It means that sum of forces is equals to zero. And then when you sum the forces in the direction of the inclined plane, this one to the right, the other one to the left, it means that these two will end up being equal. Okay, first part. What is the rate at which gravity does work on the skier? Assume the mass of the skier is 75 kg. Okay, rate at which work is being done. We know it's work done divided by time. So that is what work done is. We know what the mass is. The mass is given to us as 75 kgs. Okay, what else are they giving us? The only thing they've given us is the record speed that this skier achieves. Now, we need this in meters per second. So let's convert that to meters per second. We have 203.1 kilometers per hour to meters per second. We know we convert first the kilometer, that's in 1 kilometer. We have 1,000 meters. And in 1 hour, we have 3,600 seconds. So that the hour and the hour cancels, the kilometer and the kilometer cancels. So you're looking at 203.1 by 1,000 divided by 3,600 seconds. What will be the answer here?
Uh, 67.7.
Yeah, so this is meters per second. Divided by the time. But what force are we looking at here? The question in part A is specific, the force of gravity, or the force due to gravity. The force due to gravity that causes the object to slide down, we saw to say it is the component along the length of the inclined plane. And we saw that component was mg sine theta. So this is the component that actually does work as the person or the skier slides down. So that is what we're going to put where we have force. So we get mg sine theta where we have force. But the other side, we still have displacement. And we still have time. But the question does not tell us how far down the skier actually slides. Neither does it tell us how long it takes the skier to reach the foot of the mountain. What do you think we're going to do, or how are we going to deal with the two terms, the displacement and the time? What do you guys think? How are we going to deal with the two terms? All we know is that this skier achieved that record speed of 67.7 meters per second. It was 0.7, right? Yes, it was. That's all we know. And the mass of the skin and what theta is. Anyone to try this? Well, you have to see that actually, yes.
How about using the velocity that we have as since it's say 67.7 meters per second, we use that as a distance, and the time, since the time is saying per second, we use that as the time.
Yes, exactly that. So you can get your speed. The speed is 67.7 meters per 1 second. Yes,
Sir,
please.
I think the speed is 56.42, not 67.
56.42.
Yeah.
Can you guys verify that?
Yes, it's 56.42.
Okay, great. So yeah, so what we're saying here is, just as Regan was saying, so the speed is 56.42 meters per second, per 1 second. So if the distance was 56.42, then it means that the time has to be 1 second. So this is one way we can look at it. Or I think I once wrote you guys a formula to say, just by looking at force times displacement over time, we can find the velocity. So we can use the velocity to calculate velocity and the force, they have to be in the same direction. Or even if they're not in the same direction, then they have to be parallel, or at least in the same axis. So they have to be in the same direction. And here we see that they are actually in the same direction. By using only the component of the by using only the component of the force, which of the weight, which is in this direction, notice that my distance or the velocity is also in the same direction. Observe that in this case, the velocity and the force are in the same direction, meaning that this approach can also work. So again, you can use the approach that Regan described for just here saying if the distance is 56.42, then the time is 1 second. That will work as well. So let's substitute. We saw that we have mg sine theta multiplying the displacement over the time. So the mass is 75, g is 9.8, then we have sine 51, multiplying the displacement, we saw to say this is going to be 56.42 over 1. So do the math here, what will be the answer?
It's 2,207, 227
Point?
point two three.
Okay. This is power, so the unit is going to be the watt. Let's say this is let's say this, just mute yourself, please. Mute yourself, please. Grace, can you mute yourself? Okay. So let's confirm and see if that answer matches the one they gave us. Look at that. Exactly as they gave it. 30, that's 32,227 joules per second. We know the joule per second is the same as the watt. So that's exactly what we expected. So we found the correct answer. Okay, that answers A. Now, B is actually the complication when it comes to this question. B is what makes question 4 a two-star question. So let's see how we find out, or how we solve for B. But what are they saying in part B? Well, in part B, they're saying, what is the rate at which sliding friction does work? Assume that the coefficient of friction is this. So they are looking for the rate at which sliding friction does work. So how do we find that? Well, a little bit tricky. And observe that in C we have the rate at which air friction does work. So that is also coming. Just keep that in mind. So, well, to find the rate at which sliding friction does work, here's what we need. First thing is, so to find the rate, which is just the power, we need the work done by sliding friction divided by time. So the work done by sliding friction, it will have to be the force of friction. This is sliding friction again, multiplying the displacement through which the sliding friction was acting, then divided by the time. So let's first find the sliding friction that was involved in this motion. So how do we find that sliding friction? Well, lucky us, they gave us the coefficient. Now, if we are given the coefficient, how do we proceed? Well, with the coefficient given, we know to say frictional force has a direct relationship to the coefficient of friction. That is, the coefficient of friction is equals to the force of friction itself. Let me distinguish the two. Let me say friction. Let me not say capital F. Let me say friction sliding divided by the normal force. So this is the expression connecting the sliding friction to the coefficient of sliding friction. So from here, if we wanted to find, let's get the coefficient is, where is it? That's 0.03. Okay, so the coefficient given as 0.03, so it implies that from this expression, frictional force sliding divided by the normal, this implies that the sliding friction is equal to the coefficient of friction multiplying the normal force. So this is now what we have. So with the coefficient given, the only thing missing here is the normal force. If we know the normal force, then we can easily find what the sliding friction is. But how do we find the normal? Well, we'd have to go back to our inclined plane and remember how we handle forces, or specifically an object on an inclined plane. We know to say the weight can be split into two parts. It will have a vertical part that goes like this and a horizontal part that goes like this. We already used the horizontal part of the weight, the mg sine theta, in the previous calculation. The part of the weight that goes perpendicular to the inclined plane, we know that will be given by mg cos theta. Now, the normal force here will actually be a force that comes perpendicular to the surface, running from the surface onto the object. So the normal force will be going in that direction. So in this case, of course, if I was to complete the free body diagram, this side you still have the force of friction, which goes in this direction. So the force of friction I'm putting here, it's a combination of the sliding and the air friction. But if you sum forces in the vertical axis, of course here, the vertical axis is this one, and the horizontal axis is this one. So if you sum forces in the y-axis and equate to MA, we see that there are two forces in the y-axis. The normal going up, so the normal becomes positive. mg going down, not just mg cos theta going down, so that becomes negative. But in the vertical axis, the object is not going up, the object is not going down, implying that the acceleration there is zero, which makes the right-hand side here to be zero. So that we conclude that the normal is just equals to mg cos theta. We know what the mass is. The mass is 75. We know what G is, 9.8. We know what theta is, 51. We see that this will give us what the normal is. Can you evaluate this? What will be the answer here?
See, 462.55.
Okay, so that becomes the normal force. This implies that the sliding friction, which was equals to the coefficient multiplying the normal force, this now becomes 0.03 multiplying 462.55. So if you do this, what becomes the answer?
This is 13.88.
13.88. So this becomes the sliding friction. Now, to find the rate at which the sliding friction does work, which is the power, we need the work done by the sliding friction, which is the force, the friction sliding, times the displacement divided by time. But it's the same idea like in the previous case, where we can take the displacement to be 56.42. And if we do this, then time has to be 1 second. We still use the same velocity because it literally is still the same object. So that was 56. Was it the one? Yeah, it was 56.42. So we'll still use those two. So we have the sliding friction, which is 13.88 by 56.42, then divided by 1 second. So if we do the math, what are we getting here?
Seven hundred and 82.91.
So this is what we're getting. Let's see, does it match what they wanted us to find? Guess what? 783. We found 782.91. To 3 sig, we see this is 783, the exact thing. So we found exactly what they wanted. Now, I just want to mention one thing. See, if you wanted to be strict with your calculations, you might have said that, okay, our object is sliding downwards. So you say our object is sliding downwards. So the force is in this direction. The frictional force we're using here is actually backwards, or not even that. You could have said that the frictional force, which is the force doing work now, it's in this direction. This is the direction of Fs. The displacement is a downward displacement. So the displacement is in this direction. Because the two are in opposite direction, you might as well have done this calculation with a minus 13 to say the force is in the opposite direction, multiplying 56.42 divided by 1, the time. This would have given you the same answer as this, but just a negative. This would have just emphasized that the work done by force of friction is negative, not necessarily that the work is a vector, but to just tell you that the work that friction is doing is such that to reduce the energy of the system altogether. So if you calculated the way we did, such that it comes negative, should I have to combine or to find the overall work done by all these forces, I must keep in mind what was reducing the energy of the system and what was not. And here, force of friction is reducing the energy of the system. So in combining, I have to recall that this has to be negative so that it shows that it's energy lost by our system. Okay, I thought I just have to mention that as well. But it's okay, you can give it as a positive value. But just remember, if you have to combine it with anything, then most likely you have to remember the sign there. Okay, the last part was the work done by the air friction. Where is it? Here. What is the rate at which air friction does work? And again, they've given us an answer to compare with. The rate at which air friction does work. So just like all the other cases, the rate at which air friction does work, it's still power. Work done divided by time. How do we actually do this? Well, first and foremost, if you can find the force due to air friction, then you can just multiply it with the distance again times time. Again, we still record that this is 56.42 if the time is 1 second. But the question problem is with that one there. So how do we find it? Or maybe is there even an easier way? Well, unlike sliding friction, where we were given the coefficient of sliding friction, for air friction, we're not given anything. And really, we never even do or look at calculations on how we find it. So we have to look at what else are we given in this question. And what I mean is the question told us one thing. It told us that at this velocity, the weight causing the object to slide down, and remember the weight was mg sine theta. This weight was balanced by the friction, and it specified that the friction, when they say friction, they mean the friction sliding and the friction due to air. So these two are actually balancing, okay, not that color. These two are actually the ones balancing balancing out with that weight there. What does this imply? See, these two put together, they are the ones that are creating this overall frictional force that is being equal to that weight there. What does that imply? Well, if you added the forces in the horizontal axis, because they are saying they balance such that the acceleration is zero or the object moves with a constant velocity, when you get the summation, this is equals to 0. If we take down as positive, then you have mg sine theta as the positive one. Then the other two become negative. So you have minus the force of friction sliding minus the force of friction due to air. Then this has to be equals to 0. You see that now the problem becomes very easy because mg, this is 75 times 9.8. Then you have sine 51. Then minus force of friction. This is I wrote FF. This is sliding friction. And sliding friction, we found it earlier on. Where is it? Here, 13.88. So that is 13.88. Then next up, minus force of friction due to air resistance. So we have this. It's the only one that we do not know. So the air resistance goes the other side. So what will we get when we evaluate these two?
See, 550,
That's 5 what? Getting a lot of noise in your background. Try to type your answer.
I'm saying 557.32.
7.32
3,
like this.
yes.
Okay. So the air friction is 557.32 newtons. See, we have found the missing piece of the puzzle, and this is where we were. And if we actually know that 557.32, then we can do the multiplication. This was 56.42 32 divided by 1. What are we getting if we do this?
31,000 444.12.
Okay. Now, is this what we expected? Let's check. 31,444. Where is it? Guess what? It's the 1. So we found the correct answer. Another way that you could have used to find the same thing, you would have started first by finding the work done, not even this. You'd have just done, I think we already have both. You'd have just done the work done by the force of gravity, which is this one. The work done by the force of gravity minus the work done by the force of friction, sliding. Yeah, minus this one. Can you try this? The work done by the weight minus the work done by the sliding friction. It should give you the same answer. So that's 32,227 minus 782.91. Are you getting the same answer? What are you getting?
The same one.
The same answer. Yeah. So both would have given you the same answer. I preferred to show you this because it actually helps you understand exactly how the answer comes out. Okay, so this is how you work out this question. Do we have any questions from this one? Okay, so yeah, that's great. So hope you guys found this helpful. I have recorded this, so I will be able to share this. And if you guys were actually to be a lot in this class, then it means that I'll be willing to start teaching you math as well for free. So invite your friends to join us. When I upload this, I'll leave all the links in the description in case someone wants to join us. So invite your friends, guys. Let's end here. Have a good night, guys. Keep warm.
So I also kindly asking for yesterday's recording. I was not part of it. I don't know if you've uploaded it, but if you haven't, please upload it as well.
No, sure. I'll do that.
Thank you.
All right, bye.